Okay, so this is a key to section 8.1, part 3. Um, and number one, well, uh, let's see. You solve the system, then it says, um, is the system consistent, inconsistent, or dependent? So you want to answer those questions as well. Okay, so number one, though, you want to solve the system by either substitution or the addition method. So um, let's go ahead and in this particular part, let's go ahead and use um, substitution. Now, substitution would be easy to use because the variable x is already by itself. So that would be the most efficient method would be substitution. If you want to do the addition method, you'd have to bring everything on one side or put in standard form. Put all the variable on one side, the constant on the other. Make sure it's aligned. So by substitution, which is a more efficient method here, this equation already has x by itself. You see that? So basically, you're going to do step 2, so which means you're going to substitute x equal negative 5y minus 4. So you can substitute this expression into the other equation for x. All right, so into this other equation, you're going to substitute negative 5y minus 4 into x, because that's what x equals. So we're going to get this. We're going to get x, which is this, negative 5y minus 4, minus 4y equal 23. And so now we combine like terms. A negative 5y and negative 4y is a negative 9y minus 4 equal 23. Adding 4 to both sides, I get negative 9y equal 27. And then dividing both sides by negative 9, I get y to be negative 3. So I found the y-coordinate of my solution. So the y-coordinate of my solution is negative 3. Now we've got to find x. So we're going to find x. So find x. So we're going to substitute y equal negative 3, which I just found, into one of these equations. So it's easy to use the first one right here. So into x equal negative 5y minus 4. And the reason is because x is already by itself. We're trying to find x. So I'm going to get negative 5 times y. We're saying y is negative 3. And then subtract 4. Order of operations, I multiply first before I subtract. So that'll be positive 15 minus 4, which is 11. So my solution is 11, negative 3. All right, so that was done by substitution. Now, if you wanted to do this by the addition method, here's what you would have. So this is number 1 by the addition method. So doing this by the addition method, you first of all have to rewrite this in standard form. So you're going to say x and then bring the negative 5 over. So you're going to say x plus 5y equal negative 4. And then x minus 4y equal 23. Okay? All right, now we got to eliminate one of the variables. I'm just going to go ahead and let's go ahead and eliminate the x's. You'll notice that the coefficients of the x's are 1, so the least common multiple of 1 and 1 is 1. So we already have a 1. We just got to make sure that one of these is a negative 1, though. So we're going to eliminate the x's. So let's just eliminate the x. Now, if you wanted to eliminate the y's, you would the least common multiple of 5 and 4 is 20. One of these is already positive, one's already negative, so all you have to do is multiply the first equation by 4, because 5 times 4 is 20, and multiply the second equation by 5, because negative 4 times 5 is 20. And then use the addition method. Let's just eliminate the x's. So I'm going to go ahead and rewrite this over. X plus 5y equal negative 4. X minus 4y equal 23. So adding right away is not going to help. Okay, so what I'm going to do is, and it doesn't matter which one, I'm going to go ahead and multiply this one by negative 1. And remember, the reason I'm multiplying by negative 1 is because I need these to be opposites. That's a 1x. When I multiply by negative 1, this becomes a negative 1x, and when I add them, it becomes 0. All right, so I'm going to distribute the negative 1 through here, so I get a new system that looks like this. So I didn't do anything to the first equation, so it stays the same. So I get this first equation. The second equation, though, everything has been multiplied by negative 1. So negative 1 times x is a negative x. Negative 1 times negative 4y is a positive 4y. And don't forget the other one. Negative 1 times 23 is a negative 23. Now I can add, because when I add, the x's cancel out. X and a negative x is 0. 5y plus 4y is 9y equal, and then that's going to be a negative 27. And then divide both sides by 9. 9 divided by 9 is 1. 1 times y is y, so I get y to be negative 3. All right, so I found the y coordinate of my solution, negative 3, just like we did here. All right, and then back substituting. So now we're going to find x. So we're going to substitute. We're going to substitute y equal negative 3 into one of these equations. It does not matter which one. So let's use the first one. So substitute that into this equation. X plus 5y equal negative 4. So wherever you see the variable y, I plug in negative 3. So I get x plus 5 times negative 3 equal negative 4. X minus, that's a 15 here. X minus 15 equal negative 4. Adding 15 to both sides. Combining my terms, I get x to be 11. All right, so that takes care of number 1. Now, we have to answer. You see how you did have a solution? So this would be a consistent equation, a consistent system. So this is consistent because you did have a solution. Okay, number 2. So you want to do this by either elimination or the addition method. Now, the elimination and addition method are the same thing. So I think what I meant to say was either substitution or the addition method. That's what I meant it to be. So either substitution or the addition method. So the elimination is the addition method. That I meant substitution here. So let's do substitution because substitution is easier because the y is by itself, just like we did this one. So we're going to substitute y equal 2x minus 3. So we're going to substitute this expression into the other equation where we see the variable y. I'll plug in this. So I get negative 2x plus y, which is 2x minus 3, equal 1. So negative 2x plus y, y is 2x minus 3 equal 1. Now I'll solve this equation because I just have x left. Negative 2x and a positive 2x is 0. 0 minus 3 is a negative 3. And notice the variables disappear. Now what happens is, remember, when the variables disappear, either you have all real numbers as solutions or you have no solution. Well, this is a false statement, so you would say no solution. Or no solution. And so is a system consistent, inconsistent, or dependent? Since there's no solution, you're going to say inconsistent. Inconsistent. All right? Okay. Oh, and then let's do this using the addition method. So if you want to do the addition method on this, this is what it should have looked like. So number 2, your system was this. Y equal 2x minus 3, negative 2x plus y equal 1. So you got to put the first equation in standard form. So this becomes, when you bring the 2x to the other side, it becomes negative 2x plus y equal negative 3. Negative 2x plus y equal 1. All right. Now let's go ahead and eliminate one of the variables. Let's go ahead and eliminate the y's. Eliminate y. So I'm going to see how these are already 1's, the same coefficient, so I just need to multiply one of these equations by negative 1. It does not matter which one we do that with. So I'm just going to use the top equation again. And let's see what happens. So multiply this by negative 1. So distributing the negative 1 through here, though, you're going to get a new equation that looks like this. Negative 1 times negative 2x is a positive 2x. Negative 1 times a positive y is a negative y. Negative 1 times a negative 3 is a positive 3. Second equation you leave alone. So you just rewrite it. Now when I add them, notice what happens. The x's go away, the y's go away, 0 plus 0 is 0, and that's 3 plus 1 is 4. So just like right here, the variables disappeared. You look at the statement, is that true or false? Well, this again is false. So then you would say the solution, x equal, and you would say no solution. Okay, no solution. And again, this is a consistent system. I'm sorry, inconsistent. Okay? All right, inconsistent. It would be inconsistent. No solution is inconsistent. If you have a solution, then it is consistent. Okay, number 3. It says solve the following system. Solve the following system. Okay, that sentence doesn't make sense. So it should say, I guess, solve the following system. It has solutions which are fractions. The more efficient way of solving the system is to eliminate the variables one at a time. All right, so basically, we're going to eliminate the x's first, and then we're going to eliminate the y's. So when we limit the x's, you're probably going to end up with fractions, what it's saying. And so when you back substitute, you're going to have fractions to deal with, and that's a little bit cumbersome. So it's just quicker just to eliminate the x and the y. So here's what that means. So if we eliminate the x, eliminate the x, the least common multiple of 2 and 3 is 6. So I'm going to go ahead and rewrite this. Okay, so if I eliminate the x, the multiple of 2 and 3 is 6. So I need to multiply the 2 by 3 to get 6. And I need to multiply the 3 by 2 to get 6. But I need one of these to be negative. So let's just make the top one negative. Alright, so then distribute this, and then distribute the 2 on both sides. I get the new system, which is this. I get negative 3 times 2x is negative 6x. Negative 3 times a negative 3y is a positive 9y. Negative 3 times a negative 1 is a positive 3. Over here, 2 times 3x is 6x. 2 times 4y is 8y. And then 2 times 2 is 4. When I add them up, the variables x's go away. 9y plus 8y is 17y equal. And then 4 plus 3 is 7. Divide both sides by 17. I get y to be 7 divided by 17. So I found the y coordinate of my solution. Notice it's a fraction. Now, you see, if you went back and you back substituted, find x, and you went back and you substituted in place of y, you sub in one of these equations, this number, you'd have to deal with fractions. So it's just quicker just to go ahead and do elimination again, but with the other variable. So if I eliminate the y's this time, let's see what we get. Go back to the original, though. So if I want to eliminate the y's, this is a negative 3, this is a positive 4, so these common multiple of 3 and 4 is 12. So let me go ahead and rewrite this over. The equation's over. Alright, so again, also remember that one's negative, one's positive already. So that means that see how I had to use a negative here? These numbers are going to be the same. They're both going to be positive. Okay, so to get this to be negative 12, I need to multiply this by 4. And to get this to be a positive 12, I need to multiply this by 3. And then distribute on both sides, multiply both sides by these numbers. I get a new system that looks like this. 4 times 2x is 8x. 4 times negative 3y is a negative 12y equal. And then 4 times negative 1 is a negative 4. The bottom one, 3 times 3x is 9x. 3 times 4y is 12y. And then 3 times 2 is 6. And then now if I add them, I get 9x plus 8x is 17x. The variable y disappears, and you're left with 2. 6 and negative 4 is 2. And then finally, dividing by 17, I get my solution for x. So x is 2 over 17. Okay? And so remember, when you have one solution, it is consistent, although I didn't ask it. So it is consistent. It is consistent system. A consistent system. Okay, number 4, you want to use the addition method. So again, let's just eliminate the y's. So let's see what happens. Eliminate y. So I'm going to go ahead and rewrite this over. And let's see what happens. So I'm going to eliminate the y. So this is a positive 3, this is a negative 1. So that means the least common multiple of 1 and 3 is 3. This is already a 3. I need this to be a negative 3. So I just got to multiply the every side, both sides of that first equation by 3. So I got to multiply every term by 3. So my new system is going to be negative 12x. 3 times 4x is 12x. 3 times negative y is a negative 3y equal to, oops, that's 6. Don't forget, be careful. 3 times 2 is 6. I didn't do anything with the second equation, so I just rewrite it. And notice when I add them up this time, I want you to see what happens. When I add them up, the variable x's go away, the y's go away, and I get 0 equal, and this 6 subtract 6 is 0. So the variables disappear. So remember in the previous problem, when the variables disappear, either it's a true statement or a false statement. If it's a false statement, you say no solution, and then your system's inconsistent. But this turns out to be a true statement because 0 does equal 0. That's a true statement. That's true. So that means that your solution is all real numbers. Now, don't put all real numbers in this course. In this course, they want you to rewrite it like this. So you have to rewrite this. Don't say all real numbers. We discussed that in class. You're going to say the set of x, y's such that, and then you just choose one of these equations, such that 4x minus y equal 2. All right. Now again, the reason for that is because remember these are lines. So these are lines. So that means that if the variable disappears as a true statement, that means that these lines are going to overlap. So that means that when you graph them, and whatever the graph looks like, when you graph them, this line here is going to be the same as that line. They're going to overlap. And when you say all real numbers, a lot of students get confused and they think that every number in the plane is a solution, but that's not true. The solutions are only points on the line. Okay? They're only points on that line. Now there's an infinite number. There's an infinite number of points, but don't confuse the infinite number that you would say as being anything in this plane. It's only the points that are here on those lines. So that's why we do this. So we just indicate that, yes, it is an infinite number of solutions, but it is the solutions that satisfy this equation. That's all that is. Okay, and then since there's an infinite number of solutions, we're going to say the system is dependent. Now, it is consistent. Remember, consistent means that you have at least one solution. So the question is, do I have at least one solution? Yes, I have an infinite number. So is the system consistent? The answer is yes. Is the system dependent? Yes, because we have an infinite number. Is it inconsistent? Remember, inconsistent means no solution, so you're going to say no. Okay? All right, so that's going to take care of 8.1 Part 3. So notice I did make an error here. That should be substitution or the addition method. And the wording here is bad. So basically, you're going to solve this system, and this system has fractions. So the more efficient way of solving is to eliminate the variables one at a time. Okay? All right, so that takes care of this.